Okay, so I will just continue from where I stopped. It's giving an error when I remove these parameters. So I don't know why. So I'm going to check after the class. Then I'm going to post um, the real solution. I'm going to post it into the discussion forum. So that's the bisection or the bisect method. So the bisect method simply works by when you have two guesses, and you're very sure that the uh, the root is in between these two values. Then you find the midpoint. Then you keep changing the upper limit and the lower limit depending on depending on the the evaluation. Depending on this evaluation you have, this particular evaluation, you keep changing it, then you keep narrowing it down. Then when do you stop? You just stop at when the error is less than a certain amount, or the number of iterations, or you can specify the number of iterations, so which we did. So now we're going to move on to the force position method. The force position method is very similar to the bisection method. And the difference, let me just go straight to the difference. The difference between the force position method and the bisection method is that this is our lower limit and this is our upper limit. In the bisect method, we estimated the root to be the midpoint between the lower limit and the upper limit. But in the force position method, you're going to connect a straight line. So you have XL and you have XU. Then this is the value of the function at the lower limit, and this is the value of the function at the upper limit. So you connect a straight line to it. Then where the line touches the x-axis is the estimated root of the equation. Okay. We don't even need to define the parameters in the code since we need to vary until we acquire the root. So your original equation is okay. All right. Okay, I understand what you said. But actually, regarding the other question, you are right that need to uh, we don't need to define the values in the code. You are right. You're right. But it's not supposed to give an error if I do it that way. So I'm going to check why it's giving an error. Then I'll post the solution in the discussion from later. I don't just want to waste time debugging. That's why. But in case you come up with the error-free solution, you can also post it to your class members and share it together with all of them. Okay, let's move on to the first position method. As I was saying, in the first position method, in the bisect method, you estimate the root as the midpoint between the lower limit and the upper limit. But in the first position method, you calculate the value of the function at the lower limit. You calculate the value of the function at the upper limit. Then you use a straight line, draw a straight line in between. Then the root is where the function touches the x-axis. So that's the difference. That's just the basic difference between the force approximation um, and the bisection method. They are basically the same thing. And we arrive at the root as this. So the expression for the root is given by this equation. For the bisect method, the root was given as this. For the bisect method, the root was given as this. Let me just write it here. The root was given as x, the lower limit plus the upper limit divided by 2. So this is the bisect method. So let me just delete it. But for the first position method, this is how you get the root. And I've explained it from here. So we want to just prove how we got it. So using similar triangles, so you approximate it with a straight line. So this is a first triangle and this is a second triangle. So using similar triangles, I think you should have done that previously. So the fxl, which is here, then xr minus xl is equal to, from the theory of similar angles, is equal to xr minus xa, then the value of the function a. So this is a triangle and this is a triangle. So we equate this, you equate those two equations together. Then you make x out the subject of formula because we want to calculate the root. So if you make x out the subject of formula, you're going to arrive at this equation. So I'm encouraging you to actually do the maths from this, how you arrive at this. So one more explanation of the first position root. It's this is the value of the function. This, at this point where my cursor is the true, this is the true root. This is the exact root. But the first position method uses a straight line because the function is actually a curve. It uses a straight line instead. So it's, like I said, it's almost similar. It's exactly the same thing. The only difference is that instead of estimating the roots at the midpoint, it's estimating the roots by connecting a straight line between the lower limit and the upper limit. That's value of the function, and estimating the roots here. So similarly to the bisect method, you keep iterating until you're ready to stop. So this is only what I changed. This is only what is changed um, with the bisect method. And you keep on iterating and iterating. You calculate this, which is similar. So let's solve that same problem, but using the first position method now. So you have the upper limit, you have the lower limit and the upper limit. So we calculate the root. We are using this expression now to calculate the roots now. And when we evaluate it, we evaluated the root as 14.9309. Then similarly to the bisect method, you evaluate this function. And when we evaluated it, we got a negative number. So since it's a negative number, you will set, in the next iteration, you will set the upper limit as the value of the root you calculated. So at the next iteration, we'll set the upper limit. Previously, the upper limit was 16. The upper limit was previously 16. But now we are going to set it as 14.9309 because this expression was negative. So that means that the root is in the lower subregion. So you are setting the upper limit as this. So in the next iteration, you have new values. Then you calculate this expression here. So we already know we already know this from our previous iteration. So we don't need to repeat this. So we already know this. And we already know this. So we know it from the previous, this was what we got here. So we just put in the values and you put in the values and you're going to get this. So this is our new root. Then you evaluate this expression here. When we evaluated it, we got a negative number. So a negative number means that you're going to set in the next iteration, you will set the upper limit to the value of this root. So you keep going on and on and on and on and on like that. But now we are going to calculate the error. So at the first iteration, we didn't have a previous, for the estimated error, we did not have a previous approximation because we just started. So we cannot get anything. But in case you are doing it in a code, you can just set it to 100%. So 100% means that that's like the maximum error is like 100%. But we don't know we don't know this value because we just started. So then for the true error, we know the true error, so we can calculate it. Then for the second iteration, we can now calculate the estimated error. We got 0.78, then for the true error, we got 0.09. So if you look at the error, so for the first iteration, we had 0.8. That's like, we are very, very close. Remember for the bisect method, when we started at the first iteration, we got 5%, 5.4%. So you can say that the first position method it's better because for the bisect method, it was when we got to the fifth iteration, we're able to get 0.8%. But using the first position method, like immediately in our first iteration, using the first position method, it was in our first iteration that we got 0.8. But on the bisect method, it was at the fifth iteration we got 0.8. So you can say that, okay, the first position method is better, or is faster, sorry, it's faster, because both methods at the end of the day to converge to the real solution. So you can try to say that you can conclude that the first position method is faster, but there is a caveat, and the caveat is that the caveat is when we use this example, would is not the same. This doesn't converge faster. If we'd use the bisect method, the bisect method was actually faster, is actually faster than the first position method. So we're going to go through this example. But before I do that, this is the code for the bisect method. This is the code for the bisect method. So as an exercise now, I want you to, probably when you are reading it on your own, I told you that the code for the, I told you that the bisect method and the first position method are the same thing. The only difference is how you calculate the root. So I'll be giving you as an assignment, or not even an assignment, just do it on your own. Just when you are reading, just try to uh, use the first position, write the code for the first position method. And the only thing you're going to change is this line. That's just what you're going to change. So I'm encouraging you to actually write the VBA code, or if it's MATLAB you prefer, you write the VBA code for the first position method. It's exactly like the bisect method, but for this line. So I mean, it's not an assignment, it's just, I'm just encouraging you to do that. Okay, so let me go back, continue with the lecture. Okay, so we have another example. So I was saying that given that example we did, you might you might conclude that, okay, the first position method is better than the bisect method. But when we do the same thing for this particular uh, expression here, if you do the same thing, so this is the lower limit. So the question is to use the bisect method or the bisection method and the first position method to calculate the root of um, this function. So now we have, this is our lower limit and this is our upper limit. So like I told you previously, the lower limit and the upper limit, they are going to be given to you. But if they are not given to you, you have to guess. And the way you guess is using the graphical method. So you're going to plot it. You're going to plot it. Then from the plot, you're going to make an approximation of the lower limit and the upper limit. So we start with the bisect method. So we got this as our roots in the first iteration. We evaluated this and is a positive number. So we set the root as 0.65. At the second iteration, remember, like a question somebody asked, you need to track the error as you go along. So you need to keep track of the error. For the second iteration, our lower limit is now 0.65. Then our new root is now this. You calculate the expression for this. This is a positive number. So in the next iteration, you'll set the lower limit to be 0.975. Then at the third iteration, your lower limit is now 0.75 from what you got here. And this is your new root. You evaluate this expression. We got a negative number. Therefore, we'll set the upper limit to the value of the root we got, which is 1.1375. At the fourth iteration, our upper limit is now this. So it's now 1.135. You calculate the new root. You evaluate this expression. And this expression is a negative number. So meaning that the upper limit is set to the root we calculated. So the upper limit is now this value. This is the new root. Then we'll evaluate this expression here. This expression is a negative number. So in the next iteration, you'll set the upper limit as the new root. So now let's track the error. So like you said, you need to keep tracking the error at the first, second, third iteration. So at the first iteration, for the estimated error, we don't have the previous uh, approximation. So we just set it as 100%, but actually we don't know it. But we know the value of the true error. So the true value is 1. Those for the second iteration, you have these values for the third iteration. Notice that the error is dropping, actually. It's dropping. Then at the fifth iteration, you have this error. But when you use the first position method, remember you have to compare the first position method and the bisect method. So now we have a different formula to calculate the root. So the new root for the first iteration is this value for this. Then we evaluate this expression. This expression is positive. So the lower limit is set to this root we calculated. At the third iteration, we calculate this value and which we got here. Then we evaluate this expression. This expression is positive. So you set the lower limit as the root you calculated. For the third iteration, you do the same thing. We got the roots as this. Then this expression is evaluated as this, which is positive, and therefore the lower limit is set to this. We go on with the fourth and fifth iteration. Then we track the error. Normally, as you are going through the iteration, you need to keep on checking the error, but I just decided to do it after. So for the first iteration, uh, you had 90%, second iteration 81%, third iteration 73%, fourth iteration 66%, then fifth iteration 59%. If you would, but the estimated error is much smaller. So if you'd observe, the estimated error is getting smaller, but and the true error is also getting smaller, but it's it's converging very, very slowly. And you know that the true error is much more representative of the error. So that means that this, but when we use the bisect method or the bisection method, at the fifth iteration, we had 1.6%. But for the first position method, at the fifth iteration, we're having 59%. So this is telling you that the first position method, you might think it's better than the bisect method, but there are some functions that the bisect method is not is going to be faster, is going to converge faster than the first position method. And in order to actually mitigate against this problem, there is a modified first position method. So what the modified first position method does is that it's basically going to, okay, the reason why we are having this error, first of all, not the error, the reason why we are having this very, very large error and is not converging very faster, is not converging faster than the bisect method is that the first position method has the problem of one-sidedness, of one-sidedness. What's the meaning of one-sidedness? One-sidedness being that, remember when we started with the first position method, like, you know, this is the straight line that is connecting the lower limit and the upper limit. This is the straight line. So by using a straight line, we are saying that if the root, if the root is closer to the lower limit than to the upper limit, that means that you are actually closer to the real root. Like for in this instance now, the lower limit is here and the upper limit is here. The root, the real root is closer to the lower limit than to the upper limit. So the first position method um, approximates the root to be closer to the side of where the real root is, because the real root is closer to the lower limit. So it approximates it close to the lower limit. So that's the reason it has a one-sided approach. And as we were doing the calculation, you could see that it was only the lower limits that we were changing. We're not changing the upper limits. So at the first iteration, we change the lower limit. At the second iteration, we change the lower limit. At the third iteration, the lower limit. At the fourth iteration, it was the lower limit we changed. Then at the fifth iteration is the lower limit we change. So it's because of the one-sided nature of the first position method. That's why it's giving us that error, that large error. And to the way to actually overcome that um, obstacle is to divide the value of the function at the other limit by 2. So this is the modified first position method. So it's basically what we did previously. So this is in the last example of the bisect method. I told you that you should implement the first position method in Excel VBA. So this is actually what you are supposed to replace. So this is the first position method. The root is estimated by this expression. Then similarly, we calculated the error, and it's exactly the same thing. But now we're going to calculate this expression. Then similarly, if it's negative, you are going to replace the upper limit with the root you calculated. If it's positive, you replace the lower limit with the root you calculated. Then if it's zero, that means that your the error is zero, then you can just leave. That means that you are at the exact root. So the modified position, what does it do? What it does is that divide it divides the value of the function at the lower limit by 2, and it iterates again. That means that, let me just summarize what I'm trying to say. So that means that for this particular question, we are stuck at the lower limit. We are stuck at the lower limit because the first iteration, we are changing the lower limit. The second iteration, we are changing the lower limit. Then the third iteration, we're also changing the lower limit. The fifth iteration, we're changing the lower limit. So what this is telling you that, what this program is saying is that if you are stuck at the lower limit, or if you are stuck at the upper limit, so this expression is saying that is if you are stuck, right, at the upper limit, then divide the value of the function at the lower limit by 2, then iterate again. So here it's saying that if you are stuck at the lower limit, divide the value of the function at the upper limit by 2 and reiterate. So if you use the modified first position method instead of the original first position method, you will discover that it's going to converge really, really faster than the original first position method. So let me go back to Excel, Visual Basic, and let me share my screen. Okay, so this is the modified first position method. So this is the first position method, and we include this. So this expression simply means that if you are stuck at the upper limit, that means if you keep changing the upper limit, divide the value of the lower limit by 2, then reiterate again. Then if you are stuck at the lower limit, divide the value of the function at the upper limit by 2, then recalculate the roots of the equation. So this is the first modified first position method. Then when we call it using the 4 parameters. So similar to what we did in the bisect method, it takes in 4 parameters. So this is the lower limit, this is the upper limit, this is the estimated error, and this is the maximum iterations. So you are telling me to stop if either this condition, so if the error you calculated here is less than the error you specified here, or if you've exceeded the maximum number of iterations, then you would exit. So let's run it here. So let me share my screen. Okay, so if we would run the modified first position method, so these are lower limits, upper limits, and error and maximum number of iterations. So if we run it, we'll see that it's because 1 is the original root is 1, and uh, the estimate is given by what you have here. So you're going to use, if there is a problem with one-sidedness when you're doing the hand calculation, it's better to use the first position method. Okay, let me go back to the Okay, so this is the end of the class. So I will just let me just go over it. So as I go over it again, I'm going to look out for questions. So if you have any questions, just post it. So we are trying to get the roots of equations. So this is the first part. Actually, we have three parts. And the method we considered in this lecture, the method we considered in this class is the bracketing method. The bracketing method being that there's going to be, you have to start with a guess, because for the bisect method, we had to start with the guess of the upper limit and lower limit, and we know that the error is between those limits. So these methods are called bracketing methods. And we started with this equation A, and we discovered that if we wanted to find the value of C, if we wanted to find the value of C where other parameters are given, it's not possible. So, but you can try it and confirm for yourself that the analytical solution is not possible. So we have to use numerical solution, meaning that we have to convert the problem to the root of the equation. So what's the root? The root is finding the value of a variable when the function is equal to 0. So like when I started the class, for instance, if you're asked to solve for x, you can convert it to the root by equating the whole of this, equating it to 0. So you subtract both sides by 2, equate it with 0, then you'll find the value of x. So we will reduce it to the root of the equation. So we use the graphical method. And I said the graphical method is an approximate method. So when we use the graphical method, we got 14.8. And the reason why we're able to be accurate, the actual value is 14.80001. The reason why we're accurate is because we're using a computer to plot it. But in the case where you are using your hand, you cannot be as accurate as this. So you have to use other method. Okay, somebody is asking, I resumed today because I was not getting information about the resumption. I learned some SMS. Okay, send me a mail. Oluwaleye Sukomi. Just send me a mail. I think you know my email address. You can get my email address from your colleagues in the class. So just send me an email explaining that to me, then we'll talk about that later. Okay, so we use the graphical method, and as the graphical method is an approximate method, and we use the first position, the bisect method, which we did, then the Excel VBA code. Then I encourage you, if you prefer MATLAB, actually my preference is Excel VBA, but if you prefer to work in MATLAB, I would encourage you to convert this to a MATLAB code. That's if you prefer MATLAB, because this course is numerical methods with MATLAB. But as a case of preference, I just decided to use Excel VBA. But if you are more comfortable with MATLAB, just try to convert this code into MATLAB and try to use it. But if you are okay with Excel VBA, then that's also good, because you can either use Excel VBA or MATLAB. Then we use the first position method to solve it. So this is the formula for the first position method. Then we did examples using the AND. Then we went through the modified first position method with Excel VBA. Okay, since there are no questions, that is the end of the class. So next week, we'll deal with other methods. This root of equation is in three parts. So we are just in the first part. So next week, hopefully, we are going to consider the other methods, and there's also a third part. Then we're going to go into another topic. So if there are no questions, thank you all for joining me. So this recording is going to be available. I'm going to send it out, and